All right, our next topic is going to be chemical kinetics. So how do particles move? How do they collide? What causes some of those collisions to be successful in producing reactions? Because not all collisions between particles are going to be successful in having a reaction happen. So it's all summarized by something called collision theory, which says that if particles are going to react, they have to collide, first of all, moving fast enough, meaning having enough kinetic energy to break the bonds that are already there. And we've talked about that in the last unit. We know that to break existing bonds takes a certain input of energy. So we have to go uphill in our potential energy diagram until all those existing bonds are broken. Now, once they are broken, then we can start to form new bonds, which of course is exothermic. And the reason that's important to collision theory is because you're going to have billions and billions of collisions between, billions and trillions of different molecules happening all in the same, area or the same container. So when a successful collision happens and starts gives off a bunch of energy, that energy can be absorbed by the surrounding molecules. Now they are going to speed up and they are going to collide with potentially enough energy to break their existing bonds. And so it creates what's called a chain reaction. One set of particles, gives off energy when they form their new bonds. That energy can be used to break the old bonds of some neighboring molecules, and it just goes on and on from there. Now, in addition to having enough kinetic energy, the particles also have to have correct orientation. And this just means they can't collide in any old angle and expect a successful reaction. So for example, we have this N2O molecule colliding with an NO molecule. And then if it's going to produce these two products N2 and NO2. But that can't happen unless a couple of the nitrogens, when these guys, kind of slam into each other, unless, a couple of these nitrogens have to be close enough that they can start to form some bonds once the old bonds are broken. And the same thing is true of this nitrogen and these two oxygens. They all three have to come somewhat close together. And so you can imagine a collision between these two molecules, these two reactant molecules, 99 times out of 100 is not going to result in a successful collision and a reaction, even if they're traveling at really, really fast speeds. A couple other things to know about our potential energy diagram. We already talked about, or you already saw in the previous picture there, the activated complex. That activated complex is sort of in between the old bonds that are still breaking and the new ones that have begun to form. So what you have here is, instead of the two separate molecules that came in and the two separate molecules that are going to come out as products, we have one big sort of conglomeration of all 5 atoms together, sort of semi-bonded to each other. It's a very unstable and very short-lived step in the reaction process, but that is called the activated complex. So the activated complex is the top of the curve. Activation energy refers to the amount of energy that it takes to get from the reactant energy up to that activated complex. In other words, it's another way of saying it's the energy required to break the existing bonds. Then we already have kind of looked at this, but the change in enthalpy, or the delta H, would be just the difference between reactants and products. In this case, this is an exothermic reaction, and so we have a big negative delta H because we're going down from a higher number to a lower number in terms of our enthalpy. Okay, we also do need to know a little bit about how to affect reaction rate. If we want to change reaction rate, especially increase reaction rate, how could we go about that? Well, if we look at this reaction as an example, nitrogen and 3 hydrogens forming 2 NH3s. Let's say this is our potential energy diagram. Here are some things that we could do to try to increase this reaction. And of course, the opposites of these things would be what we would do to decrease it, to slow it down, except for the last one, adding a catalyst. But let's kind of talk about these and why they work. One factor that we could affect would be increasing the concentration, the molarities of the reactants. Now, this only works if they are gases or aqueous solutions, because you really don't have molarities of solids and liquids. But in this case, we do have reactants here that are gases. So if I added a higher concentration of nitrogen or a higher concentration of hydrogen or both, I would expect the reaction to what? To speed up, right? And so why is that? Well, is that because of more collisions, which is one part of the collision theory? It says that we have to have the correct orientation, and therefore if we want the reaction to speed up, we probably want to have a lot of collisions. So, or is it going to be because of increased kinetic energy? Right? So if I'm increasing concentration, I'm really not changing the energy of the molecules, not making them move any faster. I just have more of them in a given space, and therefore a greater number of collisions, right? All right, how about temperature? If I increase temperature, what is that going to do? Well, temperature is literally average kinetic energy, so it's definitely going to increase my kinetic energy of molecules, giving more of them enough energy to overcome that hill, right? But it's also going to result in a greater number of collisions because the particles are moving faster, so therefore more of them will be able to have the correct orientation because you have more collisions. Then we have increasing surface area. So like if you take a large log, you would never start a fire with a large log, like in a bonfire or a fireplace. You want to split it up into little tiny pieces. And what that's going to do is increase the surface area. It's going to allow more oxygen to come into contact with that wood that you're trying to burn, right? So increasing surface area is going to result in a faster reaction because you're going to have more collisions between those reacting particles. And then the last one is adding a catalyst. So a catalyst does this. If you look at the potential energy diagram, it's kind of a different thing. It actually provides a slightly different pathway for the reaction to happen. And that pathway is actually going to have a lower activation energy. We'll talk a little bit about this later on, but for right now, just understand that if a catalyzed reaction, and you talked about catalysts a little bit with enzymes in biology class, these are substances that are a part of a reaction, but they don't get consumed. And so that allows them to get reused over and over and over and over again, thousands and thousands of times. But essentially, because they're not getting consumed, they're not, we're not changing the reactants or the products. We're just, again, providing a little different pathway for the reactants to get to the products. And then if that pathway has a lower hill, a lower activation energy, then that is going to result in a faster reaction, more successful collisions of particles. Okay, and the other thing we need to talk about is rate. How do we measure rate? How do we express rate? So we're going to call this part 2, rate of a reaction. Now we're going to define rate, reaction rate, as a change in concentration of substances in a reaction over time. So if I have this reaction, I could describe the rate of this reaction according to an increase in the concentration of oxygen. So I could write it this way: rate is equal to change in concentration of oxygen over change in time, or you could just say time. So change in concentration of oxygen, we're going to say it increases, and that's because oxygen is a product. So oxygen would start at 0 and go up, right? So the rate of this reaction could be defined as how quickly it increases in oxygen concentration. We could also look at it in terms of the rate of decrease in the concentration. And by the way, these little brackets mean concentration of, or molarity of. So we could look at rate in terms of the decrease in N2O5. So N2O5 is being used up by this reaction, which means it's going to go down in concentration. So that's why we're talking about decrease in concentration. So the longer we let this reaction happen, the less N2O5 we will have. Now, if I look at this reaction, you don't have to rewrite this. It's the same reaction. If we wanted to compare or relate the rate of oxygen formation to the rate of N2O5 decomposition, how would we go about that? Well, it's going to look something like this. So it's very similar to what we just saw, only you don't see the word rate written anywhere. It's change in concentration of oxygen over time is equal to negative 1/2 of change in concentration of N2O5 over time. So let's talk about why it's negative on this side. And that's because if we want these two to be equal to each other, we know that oxygen is going up in concentration, so that would have a positive value. And we know that N2O5 is going down in concentration because it's a reactant, so it would have a negative value. So taking the negative of it would turn our answer positive, right? The negative of a negative. Now the 1/2 is because for every one oxygen being formed, we actually have to consume 2 N2O5s, which means that N2O5 would be decreasing twice as fast as O2 is increasing. It would take 2 of these molecules to create 1 of these. And notice we could be talking about the NO2, we're just not. But just focusing on these two, that's the relationship. So that's why I multiplied the N2O5 change in concentration, not just by -1, but by negative 1/2. And that's going to allow these numbers to end up being equal to each other. We're not going to plug in numbers. We're not going to calculate anything with these. I just want you to see that oxygen would be increasing as N2O5 is decreasing, hence the negative sign, and that there is that 2-to-1 molar ratio in the balanced equation, which is why I had to multiply the N2O5 by half to set them equal to each other. Okay, so go ahead and, all right, so here's one for you to try to see if you can do this on your own. A different equation, nitrogen and hydrogen coming together to make NH3. Write the equation that relates the rate of production of NH3 to the rate at which hydrogen is used up. So go ahead and pause, look at your previous example, and see if you can write an equation for that. All right, so hopefully you came up with something like this. 1/2 change in NH3 over change in time equals negative 1/3 change in concentration of H2 over change in time. So again, the NH3 is getting produced at about 2/3 the rate that hydrogen is getting used up. So that's the reason for the two fractions. And then we have the negative on the hydrogen because it is a reactant.